Okay, now we have the second part of this lecture, mathematical preliminaries. You will have sets, functions, relations, graphs, and proof techniques. Number one, sets. The set is a collection of elements. You will have, as you can see, A is equal to 1 to 3 and B is equal to train, bus, bicycle, and airplane. So we can write 1 as a member of A, but for the second case, ship is not the member of B. As you can see that ship is not the part of set B. Now these are different set representations. In first case, you can see you have finite number of elements in the set, and for the second case you can also see that you have finite number of elements there. For second case, you can see that infinite set, here another representation, that is S is equal to J colon J greater than 0. This is another representation. This could be read as S is this set of J, and such that J is greater than 0 and J is equal to 2 multiplied by K. That shows that it is a set of even numbers for some K is greater than 0. So you can say that it is non-negative and even set. Now we will have another example for a universal set. Let's say we have numbers from 1 to 10, and a set A comprises of 5 elements, 1, 2, 3, 4, 5. So A is the part of universal set. Now these are different set operations. We have set A 1, 2, 3 and B 2, 3, 4, 5. And you are performing the union operation, then you will have all the elements, but you will consider repeating elements once. As you can see that 2 and 3 are elements, those elements which are part of both sets A and B respectively. And intersection, now A intersection B, now you will have common elements between both sets. Now the difference A minus B, now you will have those elements which are only part of A, not common elements. So you can see that 1 is the element that is only part of A, it is not the part of B or common elements. Like you can see 2 and 3 are the common elements, so that's why A minus B is having only element 1. Now B minus A, you will have 2, 3 are the elements which are common. Now you will have only 2 elements, 4 and 5. Now complement is the opposite. If you have a universal set 1 to 7 and you have a set A 1 to 3, then its complement will be the elements except A elements. Like you can see that 4, 5, 6, 7 will be A complement, and a complement of a complement will be again without complement, as you can see, which is equal to A. Now even integers, complement of even integers will be odd integers. As you can see, from 0 to 7, if you have even number 0 to 4, 6, then its complement will be odd numbers 1, 3, 5 and 7. Now De Morgan law, I think you are familiar with it, so I don't have to discuss. Empty or null set is that's the representation of empty set. The complement of empty set is the universal set, a set consisting of all the elements. So S union empty set will be equal to S. Suppose S is some set, then S intersection of phi is equal to phi, because there is no element common. So S minus phi will be S and phi minus S will be phi respectively. Subset with two basic sets A and B. Actually this symbol actually tells that A is equivalent and subset of B in the first one, and proper subset indicates that it is only the subset. Subset means it's a part of another set. As you can see that A is the part of set. So disjoint sets, any set whose elements are not common. As you can see that A consists of 1, 2, 3 and B consists of 5, 6. So A intersection of B will be equal to phi. So for finite set, 2, 5 and 7. So set cardinality tells that the set size is 3. As you can see that we have 3 elements. Now power sets A, B, C, 3 elements in a set S. So first you can take the power of 2 to check that how many possible combinations are there. So if you have 3 elements, then 2 raised by 3 will be equal to 8. So you know that you will have 8 possible combinations. As you can see, phi, A, B, C, A, B, A, C, B, C and A, B, C respectively. So these are the 8 elements. Now Cartesian product. So now you will have different combination for multiplications. Sorry for interruption. So you have different products for each element once. As you can see that 2, 2, 2, 3, 2, 5, 4, 2, 4, 3 and 4, 5 respectively. So you can check this multiplication factor by only multiplying the number of elements with each other. As you can see, you have 2 elements in A and 3 elements in B. So 2 cross 3 will be 6. So you can see you have 6 combinations here. So you can generalize for more than 2 sets. Respectively, you will multiply the number of elements of respective sets. Over functions, you have domain and range. Let's we have a set A and B. So f of 1 is equal to A, let's suppose. So 1 tends to A, 2 tends to B, C, 3 tends to C. So overall you can see the function A tends to B here. So then f is a total function, otherwise f will be considered as a partial function if it is not tending towards any specific element. So these are the relational operator we will use here. We're having the 3 multiple cases here. Let's say we have relation with x1 with y1, x2 with y2. So respective subscript will be considered here, where x is the element, xi is the element related to A set, and yi is the element related to B set. So here you can see that both denote xi or yi to denote A, B as a member of relational operator. Let's suppose you have a relational operator greater than, then you can watch here that 2 is greater than 1. These are different examples of this situation. 3 is greater than 2 and 3 is greater than 1. These are equivalence relations that are normally used. Number 1 is reflexive. With reflexive, it will reflect the same element. And it is symmetric. Either you have a relation x relation with y or y relation with x, it will be considered as same operation, or it will generate same result. Number 3 is transitive. X are y and y are z. Like you can see that the relation of x is with y and the relation of y is with z. Then you can say that the relation of x could be considered with z. Like you can say a group of students, 3 students that came together. So when one comes, then I will assume that second and third will also join them. So for example, uniqueness operator, you can see that x is equal to x and x is equal to y, y is equal to x is equal to y and y is equal to z. Then again, according to my example, x is equal to z. So for equivalence relations, or we have equivalence class of x with y such that x relation is with y. So let's suppose you have these different combinations: 1 1 2 2 1 2 and 2 1, 3 3 4 4 3 4 and 4 3. So for equivalence of 1, you can consider the equivalence relation 1 and 2, like the greater number will be considered here. 1 and 2 is greater than 1, and in the same way equivalence class for 3, the greater one is considered 3, 4. You can see the graphs, node, edges. These are basic concepts that should be clear at this stage. Number 1 is node. Node is a point. It could be a junction. Edge is a line that joins any 2 nodes. Now you can see 5 nodes are here, A, B, C, D, E, and you can see different various edges here, like A, B, B, C, D, E, C, A, C, E, G, C, E, B, and E, D respectively. Now, this is the labeled graph for different edge relations. You can label according to your own thought. As you can see that here you have different numbers. 1 and 2 is repeating, 6 is repeating, 3 and 5 respectively. A walk is a sequence of adjacent edges. As you can see, if you want to reach from E to A, you can follow this walk: E to D, D to C, D to and C to A. You can also take the path, another path, like E to B, B to C, and C to A. Path is a walk where no edge is repeated. A simple path where no node is repeated once. Cycle, a walk from a node to itself. Like if you are starting from base B, then you will move towards C, A, and again towards B. The simple cycle is only the base node is repeated, as in our case. Euler tour, a cycle that contains each edge once. Any cycle. You can have multiple Euler tours. Next is a Militant Cycle, a simple cycle that contains all the nodes. You're taking all the nodes, as you can see from base E, you are moving towards D, C, A, B, and again towards A. Now finding simple paths. Let's say you have a origin C, so you have two ways from here towards A, towards E. For second step, you can take C to A and A to B. And for the second case, C to E, you have two possibilities: C to E, E to B, and CE and E to B. For step 3, you can take third step for the first case, that is C to A, A to B, and A to then B to E. And for the second case, you have no third option, because both paths are joining again towards origin. Now for the step 4, you can see another length is added for the first case, that is C to A, A to B, B to E, and then E to B, then E to D. It is the longest path possible here. Here you can see the trees, three parts: root, leaf, the second stage, or if you are thinking towards inheritance, then it could be represented as parent, then again for the child, and so on. So these are the levels: level 0, level 1. The more far you are from root, the levels will increase. Binary trees represent two possible outcomes, as you can see from the root, two outcomes, and from further you can see for all the cases you will have two outcomes. So this is our lecture for today. Inshallah we will meet soon in the next lecture. And now I am waiting for your questions. As you know that our class time is from 5:15 to 7:45. So I will assume that you are taking my class from 5:15 to 6:15, and then onwards you will post the questions in this group, and I will answer them accordingly.